In this video, we'll be looking at how to use the sum and difference formulas for sine, cosine, and tangent. So before I show you what the sum and difference formulas are, I want to show you why they exist. Typically, when students see those sum and difference formulas, they think that they're needlessly overcomplicated, but it turns out they're extremely necessary. So when we start, let's go ahead and take a look at the sine of 90 degrees. Now, we've done the unit circle, and we know that the sine of 90 degrees is going to be the y-coordinate up here. So the sine of 90 degrees equals 1. So that is something that we should already know. We know this is a true fact. So let's find out what happens if we turn this 90 degrees into the sum of two other angles. So let's, instead of writing it as sine of 90 degrees, let's do the sine of 60 degrees plus 30 degrees. So we know this is still the sine of 90. This should still equal 1. But here's why we need the summation formulas. Most students will say, oh, well, that means that I can distribute this trig function. I'm about to show you that you cannot do that. You cannot distribute the operation sine across into there. That is not allowed, and I'm about to show you why. So let's pretend like we're not the best of students, and we did do that. So we're going to go into imaginary land. This is something that a bad student would do, but you guys are all great students. Imaginary land. So here we're in our heads, and we are now finding the sine of 60 degrees plus the sine of 30 degrees. So we are currently being not great students and distributing that operation there. Well, since we are good students, or since we know our unit circle, we know that the sine of 60 degrees is the y-coordinate up here, a small distance in the x direction. Let me make that more visible. Small distance in the x direction, large distance in the y direction. And then for 30 degrees, so this one's 60 degrees, for 30 degrees, we have large distance in the x direction, small distance in the y direction. So the sine of 60 degrees, this one here is for 30 degrees, is root 3 over 2, plus the sine of 30 degrees is 1/2. So we cannot add a radical and a whole number like that, but we can add fractions, especially since they have the same denominator. So we have discovered that the sine of 60 degrees plus the sine of 30 degrees is root 3 plus 1 over 2. Which is not 1. So this is why we need those sum and difference formulas, because we can't distribute that operation. So a lot of mathematicians went through and they tried to find a proof for those summation formulas and find a way to actually find the sine of some angle plus some angle. And that's what we're going to see on the next slide is the fruits of their labor. These are going to be the sum and difference formulas that we'll be using. So these formulas do look pretty complicated, but let's go ahead and break them down a little bit. So a lot of students think that they're going to have to know both the sum and difference formulas. But if you look at it carefully, you can actually see that the sum and difference formulas are very, very similar. And that's because of those even and odd functions for sine and cosine and tangent. So if you look at it, we've got the sum of a plus b has a minus sign between them. But if you look down at the difference formula, the cosine of a minus b has a plus sign between them. So they are the exact same formulas, except you've got a different operation there in the middle. And that holds true for all of them. The sine of a plus b has a plus sign between these two terms. Sine of a minus b has a minus sign between those two terms. And last but not least for tangent of a plus b, this one's a little bit more complicated, because it turns out you have two operations there, but both of them do switch when you change it to a difference formula. And again, that has to do with those even and odd functions. But basically, as long as you know only the summation formulas, the difference formulas are where you switch all of those signs. So you don't have to memorize 6 formulas, you just got to know 3 of them. So here's our first example problem. We've been tasked with finding the sine of 105 degrees. And we're going to go ahead and use both the summation formula and the difference formula. So first thing I need to do is I need to turn this problem into some form of a summation. So instead of writing sine of 105, I'm going to write the sine of something plus something. Now I want to make sure that this problem is still equivalent to the sine of 105 degrees, which means I need to find some a and b value such that when they're added, they get 105. Now there are literally infinite possible answers to this. You can say 104 plus 1, you can do 100 plus 5, there are infinite answers. But there are only a handful of answers that will help us solve this problem. So the goal here is we need to pick an a and a b that show up on the unit circle. Because if you look in the next step, we're going to be finding the sine of a. So if I had written it as, let me go back, so if I had written it as 104 and 1, I don't know what the sine of 104 is, and I don't know what the cosine of 1 is. So I need to choose values that I do know the value of. Well, we know all of the values on the unit circle. So if we do 45 degrees and 60 degrees, then it becomes a problem that we can solve. So we know the sine of 45 plus 60 degrees is the same as the sine of 105. So we're going to go ahead and substitute into the identity. The sine of, now we write 45 degrees, plus, sine of 45 degrees times cosine of 60 degrees. Now there's the plus sign. Cosine of 60 degrees, cosine of 45 degrees, and the sine of 60 degrees. Well, now that we know these values, we can go ahead and plug them in. The sine of 45 degrees, according to the unit circle, is root 2 over 2 times the cosine of 60 degrees. Well, the cosine of 60 degrees is the small value, so 1/2, plus cosine of 45 degrees, that is root 2 over 2, times the sine of 60 degrees, well, that's the y-coordinate, root 3 over 2. Well, now we're following order of operations. This is an arithmetic problem. To multiply fractions, you just multiply straight across. So root 2 over 4 plus, well, now to multiply these radicals, because they're both underneath a radical, you can multiply the insides. So it becomes the square root of 6 over 4. Now we're adding fractions. You cannot add the insides of this radical. You cannot add the insides of those radicals. The only way to add radicals is if the insides match. So we're just going to simply write it as root 2 plus root 6 divided by 4. So here we've solved for the sine of 105 degrees. We're going to go ahead and do the exact same thing, but we're going to use the difference formula. Since we're solving the exact same problem, we should end up with this answer again. So let's go ahead and try that out and see what happens. Well, we're going to start this problem off the same way we started it before, but this time, instead of finding two numbers that when added give you the sine of 105, now I need to find two numbers that when subtracted give me the sine of 105 degrees. Well, in this case, there are, again, many different possibilities, but again, we want to choose something that's on our unit circle. So again, you've actually got quite a few different options. If you look at your unit circle, there are a lot of different ways that you can subtract the numbers to get 105. I'm going to choose something minus 45 degrees. It's usually something minus 45 degrees in these types of problems, but again, there are many different ways to do it. So it turns out 150 degrees minus 45 degrees gives you 105 degrees. Which means now I have my a and my b value. I can substitute it into the equation. The sine of 150 degrees times the cosine of 45 degrees minus the cosine of 150 degrees times the, sine of 45 degrees. Ooh, almost ran out of space. Now it's just a game of solving it. The sine of 150 degrees, well, 150 degrees is over here, where I have a small y-coordinate. times the cosine of 45 degrees, well, that's root 2 over 2, minus the cosine of 150. Here's something to be careful of. Cosine of 150, we're now in quadrant 2. I have a negative root 3 over 2 as my x-coordinate, and the sine of 45 degrees is root 2 over 2. We're again at just an arithmetic problem. 1/2 times root 2 over 2 is root 2 over 4, minus a negative turns us into a positive. Multiplying those insides of the radicals, root 6 over 4, lo and behold, we end up with the exact same answer. So this is one way you can use those sum and difference formulas to solve types of problems. Let's take a look at another type of problem we can do. So here's another type of problem that we can do, and this one looks a little bit more confusing, but part of what makes this a little bit harder is because it's actually requiring you to pull back old knowledge. So here they say that the cosine of theta is 4 over 5, and the tangent of phi is 5 over 12. All given angles are in quadrant 1. Okay, that's a very important piece of information, because this here tells me that all of the opposite and adjacent values will be positive, so they're all greater than 0. I need to find the cosine of theta plus phi. So I've put down the summation formula here, but something that somebody might be uncomfortable with is the fact that this says a and b, and these say theta and phi. Well, it doesn't matter, they're just variables. If I'm given these two variables, I should use those two variables. So the first thing I'm going to do is rewrite this as theta plus phi, and I'm going to replace all of my a's with theta, and I'm going to replace all of my b's with phi, minus the sine of theta times the sine of phi. So now if I know these values, then I can sub in and just start solving the problem. Well, here I know the cosine of theta is given. This value right here is 4 over 5. There is no arguing that statement. So how am I going to find all of the other parts? Well, if you think back, all of these trig functions come from right triangles. So what we've been told is the angle is in the first quadrant, but we don't know what it is. We know that this angle right here, theta, has an adjacent of 4 and a hypotenuse of 5. Well, in order to find the sine of this angle, which we need right here, we need to know what the opposite side length is. Well, this is where Pythagorean Theorem comes in. We know this is a right triangle. We've got an adjacent side of 4. We've got a hypotenuse of 5. This is actually a Pythagorean triplet. 4 squared plus my opposite value squared is equal to my hypotenuse squared. If you've done Pythagorean triples enough, you know that this is going to end up being p equals plus or minus 3. Well, since we're in quadrant 1, we know the answer is going to be 3. So my adjacent is 4, my opposite is 3, and my hypotenuse is 5. This gives me a sine of theta as 3 over 5. I now just need to apply that same exact logic to the tangent of phi. So let's go ahead and do that. Again, we are still in quadrant 1. We've got tangent is 5 over 12, so we've got opposite over adjacent. Oop, that's not a D. So my opposite side length is going to be 5, and my adjacent side length is 12. Using Pythagorean Theorem, I will again come out with a Pythagorean triple, which means this side length right here, the hypotenuse, is 13. So I've got my opposite, I've got my adjacent, and I've got my hypotenuse. Cosine of my angle is going to be adjacent, 12, over hypotenuse, 13, and my sine of the angle is going to be opposite, 5, over hypotenuse, 13. So we've got all the pieces to this puzzle. We've just got to use the arithmetic to actually solve it. So let's go through and start simplifying. We've got multiplication of fractions, so I'm just going to multiply straight across. So 4 times 12 is going to be 48 over 5 times 13, which is going to be 65, minus 5 times 3 is 15, and then 5 times 13 is again 65. So plugging this in, we're just going to have to subtract those numerators and keep the denominator since we already have a common denominator. And we end up with 33 over 65. So there we have it. We have solved another type of problem here. We're going to take one more look and we're going to try this out with tangent because the tangent does tend to scare people a little bit. So here's the last example we're going to look at. So again, we're going to need to plug things in. So I'm going to rewrite this tangent of a minus b using the values that are given. So the tangent of, oh, excuse me, that shouldn't say equal. This turns into the tangent of d minus c is equivalent to the tangent of d minus the tangent of c over 1 plus tangent of d times the tangent of c. So now we've just got to find those values. Well, luckily, we were given the value of tangent of c, so we know what those values are. We were not given the tangent of d, so we do have to use that right triangle trig and figure out what the tangent of angle d is. So here is angle d. We are given the sine of the angle, which means we know the opposite and we know the hypotenuse. So hypotenuse is 13, opposite is 12. Again, I've given us a Pythagorean triple to make the practice just a little bit easier, but this ends up being 5, technically plus or minus 5, but again, we're in quadrant 1 just like the last problem. So if I want to find the tangent of d, it's opposite over adjacent, so 12 over 5. Honestly, we've done the hard part. The rest of this is all arithmetic working through it, so I encourage you guys to try and figure that out without me, but I am going to talk just a little bit as I go through this in case you do get stuck. So tangent of d is going to be 12 over 5 minus the tangent of c, which is 24 over 7, all over 1 plus tangent of d, 12 over 5, times tangent of c, 24 over 7. So my next step here is I need to actually subtract these fractions up here. So I need to follow proper order of operations as I go through this. So I'm going to find a common denominator. Easiest way to find a common denominator is to scale this one up by the denominator of the other and scale this one up by the denominator of the other. So 12 times 7 is going to be, let me say, change colors, 84 over 7 times 5, which is 35, minus 24 times 5 is going to be 120 over 7 times 5, which is 35. Down here, I'm going to do another little step as well. I'm going to multiply these two fractions. Since they are fractions, you can just multiply straight across, and you get 288 over 5 times 7, which is 35. So in this step, we've found a common denominator, and we've multiplied these fractions. So let's go ahead and continue through. The reason we found the common denominator was so that we could subtract those. So 84 minus 120 gives us negative 36 over 35. Down here, we've got to find a common denominator to add these. Well, that's an easy one. 1 would just be 35 over 35 plus 288 over 35. So now before I divide these two, I've got to finish solving this denominator. So we have a common denominator, which means that we can just straight add them. So 288 plus 35 is going to be 323 over 35. Well, now we've got fractions inside of fractions. This is where we're going to multiply by the reciprocal. You may also know it as keep, change, flip. So to help people out, we are going to keep the numerator, change division to multiplication, and flip the denominator. The more mathematical way of saying it is to multiply, so there's the change, by the reciprocal. Reciprocal is the math way of saying flip the fraction. So as we go through, negative 36 over 35 times the reciprocal, 35 over 323. Well, this is kind of nice. Those 35s cancel out, and I'm left with negative 36 divided by 323. Now the last thing that I want to do is make sure that it's as simple form as possible. So I'm going to see if there's any sort of commonality, common factor that I can pull out and cancel. Turns out there is not. So this is my final answer for the tangent of d minus c. The reason tangent is harder is because you've got all this arithmetic that you need to work with. But those are some examples of ways you can use this